So we start with corrections, and we had these equations, these nuclear equations. The first one here was silicon, and it decayed to form aluminium. So what you do when you are balancing these equations, make sure that at the end of it all, when you sum up the mass numbers on the left hand side, it should be equal to the mass number on the right hand side. For example, on the left hand side, the mass number is 27. So on the right hand side, the mass number is 27 plus 0, which becomes 27. So that means the mass numbers are balanced. Let's look at the atomic numbers. This is 14, but this is 13. So we had to add here, we had to look for a radiation which adds 1 to 13 to make it 14. And that was capturing of an electron. That was capturing of an electron. An electron, this is a beta particle. When a beta particle is added this side, remember a beta particle, the atomic number is -1. When it is added this side and it crosses equal signs, it becomes a minus. So minus followed by minus, that's how it becomes plus. So this was what it was supposed to be here. Then when we look at this equation number 2, the mass number here is 236. Then we add 1, it becomes 237. We must make sure that what we have on the right also becomes 237. However, this one is a gamma ray. A gamma ray has no effect on either the atomic number or the mass number. So when a gamma ray is emitted, the mass number is not affected, and likewise the atomic number is not affected. That's the effect of the gamma ray. So we just add this one. We have agreed it is 237. So this one is already 2 times 1 is 2, and this is 149. I mean, when you add it to it becomes 149. So 149, what is remaining for us to make 237? And it is 88. That's why the mass number is 88, where there was minus here. The atomic number here is 92 on the left hand side. So 2 times 0 is 0. So if this is 60, this one has to be 32. What do you do? You don't change the atomic number, but you go to the periodic table, which I had sent attached to the questions, and you look for, you go to the periodic table and you look for the element which has an atomic number of 32, and that element is here. It is germanium. It is the one with an atomic number of 32. So you just write that element like this. Note, you get this element from the periodic table after getting the mass number as, as this number as 32.
Why are they showing S5 chemistry?
So let us go to part B. Part B was asking, it had given you, I don't have the question here, but you can look at it. It had given you 75, no, it had given you 12.5% as the amount of the element that had decayed. So it means N which is the amount of the element remaining, is 87.5. We get it by getting 100 minus 12.5. That's how we get 87.5. Then we use our equation to help us to get the value of lambda. They had given us the time, which was 45 days. So we say 2.303. Our equation is familiar with us. We proved it the other time. N is the amount of substance of the radioactive isotope remaining. N naught is the initial mass. And we have our equation, which is that, and we get our value of lambda. Lambda being the constant, we give its units because we are dividing by 45, which is the number of days. This one is a constant. Because we are dividing mass divided by mass, you get 1. So this one on the left-hand side is a constant. When I divide by days, I get the value of lambda, which is in units of per day. Note, you should always give the standard units of that value of lambda per day before you proceed. Yeah. So T1/2, or the half-life, which they were asking for, you use our expression. T1/2 is natural log of 2 divided by lambda, and that's how we end up getting 233 days. I want to thank one of you. Rosette passed everything here, and since I have taken you through the correction of the first thing, I am sure you can be able to do the other numbers and get those answers since I've given me corrections. Whatever will not be clear, you can ask me. So, Nabum, I was the only one online. I don't know. Do you have any question on these corrections? Yes? You have a question? Now, maybe on this part.
I don't.
Okay.
No, I don't. But
Maybe,
teacher,
I'm listening. Maybe on this part, when an alpha particle is emitted, the mass number reduces by 4, and the atomic number reduces by 2. The alpha particle is a helium particle. So this is how this one becomes 228, and this is 88 here. When an alpha particle is emitted. If it is emitted here, it means it should be added on the right-hand side. So when you add this alpha particle, helium particle, plus 4 here, plus 2 on the atomic number, it still gives you this. Now, it is this X that has been formed that is going to emit a beta particle. And when it emits a beta particle, remember the mass number increases by 1. So you go to the periodic table and find the element which has atomic number of 89. And that's the element that you write there. So that is enough on corrections. Now, I had told you that we shall revise on how to determine the half-life of radioactive substance from the graph. If we have these values, say you have these values and you have been asked to plot a graph, and you plot a graph. For me, when I plotted, I got this kind of graph. This is the graph that you can get after plotting those values. So the question will always be, how can you use this graph to determine the half-life? How do you use this graph to determine the half-life? It is very simple. You see, when you plot, the graph was ending here. So the last point is this one here. This is the last point. Now, I'm assuming that you can be able to plot this graph. Now, when a question is asking you to determine the half-life, you can always get any two values. For example, this is 24 and this is 25. If I want to use this point here, 25, then I go and look for a half of 25, and a half of 25 is 12.5, which is this one here. This is my 12.5. So I count the time. I draw a straight line, dotted line, from 12.5 until that dotted line meets the curve, meets the graph. And your curve should be a smooth curve. I want you to look at that. Don't draw a graph with the stomach, which is zigzag. Your curve should be a smooth curve. You'll get marks for that one also. So if I want the half-life, for example, I can use 25, which is here, and 12.5. So I will count the time that is between. So below here on my graph, there is time. You can see below there is time here. So this is time. So I will count the time from 25. You see, 25 is exactly on my vertical axis, which is 0. So my 25 is at 0, and my 12.5 is at this point. So I will draw a straight line going down to time, and I will count this time from 0 to where my line ended. Draw a line from 12.5 until it meets the curve, then come down up to where the line meets the axis for time. Then I count this time. Up to here is 40, but look at the scale that you are using. You are using 2 centimeters to represent 5 units. So meaning each two small squares, they represent 1 unit. So if this is 40, this will be 41, this will be 42.5, and these are 4 small squares, which is 2. So it becomes 44.5. That is the half-life there. Unfortunately, this graph cannot allow you to use any other two values. For example, if I want to use 22 and I look for its a half, which is 11, you realize my 11 is not meeting the curve anywhere. So I am not allowed to use 11. So that is the challenge which is there. If I use 20, that means I use its a half, which is 10. And 10, when you go across, your 10 is not going to meet the curve. So in this question, you are only, the question is closed in such a way that you can only use 25 and 12.5. Now, but if it was not closed, let's say the curve was continuing and ending right here, then you should have at least used the two values of half-life so that you can compare to find out if the half-life is being constant. For example, after using 25 and 12.5, you could have come and used 20 and 10 and see if the half-life or if the time you got by using 25 and 12.5 is the same as when you use 20 and 10. If the time is not exactly the same, what you do in that case, you add the two times. You call the first one T1. I can call this one T1, this time taken here. Then I call the one for 20 and 10. I draw my dotted line from 20 to the graph. I draw my dotted line from 10 to the graph. Then I get the time in between here. In between, you get the time in between the line for 20 and the line for 10, and that will be the half-life. I was saying if it is not the same for the first one, if T1 is not exactly equal to T2, to get the half-life, you get T1 plus T2 and you divide by 2. You get T1 plus T2 and you divide by 2. Yes, you get T1 plus T2 and divide by 2 to get the average. Take note of that. Now, there is a question which we can derive from here. After getting your T a half, which is half-life, the way I have told you, we can ask you, the question is determine the half-life. Then the other question will always be determine the decay constant. Here you use our equation, natural log of 2 divided by T a half is equal to the decay constant. Decay constant is equal to natural log of 2 divided by T a half. Now there is a question which you always ask here. Determine the order of reaction. Now, here we can, the half-life helps us to determine the order of reaction only if it is of order 1. And how do you conclude? If the half-life is constant, if when you use the 25 and 12.5, the time you got is the same as the time when you used, let's say, 20 and 10, then it means half-life is constant. If half-life is constant for the different times, it means that reaction is a first-order reaction. That's what it means, that reaction is a first-order reaction. So that's what I wanted to say about the graph. Maybe if you have any question about the graph before I give you the assignment.
Teacher? Is it okay if we do an example?
If we do an example?
Yes.
But the example is here. Maybe I'm going to write for you its answer. The example is here. The graph is here. And its question is
okay.
Here. The problem is now I cannot write because I'm using a laptop. But I can explain to you how to get. I can explain to you how to get the half-life. Then for you, you plot a graph, and then you get half-life. Do you see this 25? You see this 25? You see this 25, and you are supposed to draw a line.
Yes.
From 25, and the line meets the graph. But now your 25 is exactly on 0, so there is no way you are going to draw a line. So the way you have drawn a line from 12.5 to meet the graph is the way you should have drawn the line from 25 to meet the graph. And the time between the line for 25 and the line for 12.5. So half-life, if you use the 22, then you use 11, which is a half of 22. And you get the time in between. For example, if you had used the 24, you'd have drawn a line from 24 to the graph, and you bring your line down. Okay? The way this one was brought down
Yes.
to meet the time, then you draw another one from 12 to
Okay.
come until it meets the what? The graph. Then you now count the time from this line of 24 to this line of 12 where it meets the time, and you count the time. That will be the half-life. But I'm saying you need to use like two values to find out if the half-life is the same. If it is not the same, then you should take the average. You should take the average by getting the half-life for the first one plus the half-life for the second one, divided by 2.
Okay.
Okay. So this is the first graph. Maybe for simplicity, you can draw it, you can plot it on your graph paper. Then if there is anything you need, you can ask me inbox and I will answer you. I have this as the assignment whereby you are going to plot this graph and you use it to determine the half-life. Same way I've told you how you do this one.